So, good evening. Whenever you will see this video, I will be starting with today's session, and welcome to the week 3 lecture, live session of electrical measurement and electronic instruments. And today we will be discussing about what we learned in week 3, and we'll be going through the assignment, previous year assignment, so that it can help you in solving the assignments of this week 3, and we will be solving some of the extra questions also, so it will help you enhancing your knowledge in this domain. uh, yeah, so before talking about assignments and extra questions, I would just like to tell you one fact. So I know that today is holiday, but you can see this as a recorded session, but I will hope that in next session you will come live for the lecture. Okay. So yeah, so you must have seen these analog meters in your measurement labs, and so this something. So one of that type is this, and it can be something like this also, where the oops, sorry. Yeah, it can be. So this is still 90 degrees. So starting from here, it is going here. So it is covering a span of 90 degrees. So you can also see like this also some instruments which have like some particular angle, not specifically 90 degrees. So variations are there in analog meters, in case of voltmeter as well as in ammeters also. You can see in wattmeters and other types of meters also. So one of this we can see here in this image, which is like this V symbol denotes voltmeter. So this kind of a fun fact, like you must have observed there's something on here. So this is just like to this part of this live session is just to like give you a good perspective of what things are written on that meter, and you should know about that. So it's a good learning. So you must have seen these kind of symbols on these analog meters. So it's like something like U, uh, opposite U type symbol, then dash, then we have 1.5, then we have something like this, and this can vary, like it depends on the type of instrument. So this actually contains a lot of information about how this instrument works and what is there inside this, and how you should use this analog meter. So I will just go through the different types of symbols and what they represent. So next time when you see such type of analog meters, then you will be getting an idea. Okay, so this means this. Okay, so if we start, so normally if we have something, let's say we have something like this. So normally these are the symbols which we can see. So this is a star here, and there can be some number inside that star, or it can be empty also. So this represents either this will be AC or DC, before like this symbol dash, or if it is AC, then it will be like, and if it is DC, it will be like this. And this symbol actually represents type of meter. So if we have, see, so this is like for this symbol, we it means this is a PMMC meter. So it is seen by a magnet, a horseshoe shaped magnet, and uh, moving, like permanent magnet and a moving coil. Then we have something like this, which is PMMC ratio meter. Then we have, yeah, so basically I'm talking about what, so this is kind of a fun fact. Okay, I should wait for 2 minutes more. Maybe people will join and I'll start. So okay, we can we can start. So yeah, basically, so this is we'll solve assignment questions and previous year assignment questions and do some extra questions. But before that, I was just talking about some fun fact, like when you go to a laboratory, measurement laboratory, and then you see these analog meters, voltmeter or current meter. So then what you see in that? So this is a typical one kind of meter, voltmeter, and this is having a scale of like a 90-degree angle scale, and you must have seen symbols like this present on that meter. So these can vary based on the type of meter. So these symbols actually contains information, a lot of information about what that meter is. And so I was talking about that. So if we see such symbols like something like this, so the first, this, if we have these dash, and or if we have a wave like thing, so that means if we have wave, that means that is a AC type meter, that it can measure AC. If we have this dash like thing, then that it means that it can measure DC. And then we have these this symbol, U shape symbol. It means basically type of meter. So this means this is a PMMC type meter. So we have various symbols for this. So this means with the cross, means this is a PMMC ratio meter. Then we have like this, so this is a moving iron meter. So if this is present on that meter, so that means this is a moving iron meter. And then we have so I will just talk about the fundamental, the basics instrument. So this is kind of a electrodynamometer. So, and if you have a ring like structure across it, then we have, so this is dynamic meter, having iron bars in it. And yeah, if you have a PMMC meter with a rectifier in it, so we will make it like this. So even the symbol can be seen. Okay, this is a magnet, and this we have a diode as a rectifier. So this, and we have a iron bar here. So this is PMMC with a rectifier in it. And if we one more symbol, so this is electrostatic symbol, for electrostatic meter. So this gap represents the capacitance, which you have seen in the first week of the lecture. So it is based on the voltage, the charge accumulated by the capacitive plates between. So that's why these two represent those things. So these are the type of symbols which we can see on the meter, and we can tell that okay, this is this type of meter. And after this we have so we have this number also. So what does this number say? So this number can be in various like methods that can be represented. It can be like this, it can be like this, and it can be like simple number also. So basically, you have heard of accuracy also. In one of, I think, week 2, you have heard about accuracy. So accuracy normally means the percentage error it can have. So if we are having a circular ring across this number, that means this is 2.5 percentage error with respect to the indicating value. So whatever the meter is reading, so there will be a 2.5% error on that reading. Now if we have something like this, so in this meter we have only this number, and it is not having any circular ring or some bars across it. So if this is a number, then we have 2.5 percentage error, but this time with respect to the full scale deflection or full scale reading of the meter. So if we have a full scale reading of 40 here in this case, so whatever, and let's say this meter is measuring something near to 20, so it will be having the actual reading will be 20 plus minus. So let's say if the reading was 20, the 20 percentage of, so into 40 percentage, something like this. So 20 percentage of full scale reading. Okay. No, 20 percentage of full scale reading means 20 plus minus 40 percentage. Okay, so this will be 2.5. This is the percentage error of full scale. So this was full scale, and this was the percentage error. So 2.5 percentage of full scale reading will be the error in this, if we have a reading like this on 20. Okay, so this means that now if you have this modulus kind of symbol on our meter, then it will be the error 2.5 percentage error with respect to the span of the meter. And this span means uh, the range of the meter. That means the will be that is like maximum value of the meter minus the minimum value. So in this case, this is like 40. So we have minimum 0, we have maximum 40. So this will be 40. But sometimes we have like 0, and we have negative readings also, and we have positive readings also. So it will be like what? So let's say this was x, this was minus x, so this will be 2x. Okay, so this signifies this. Now we have another symbol, this one. So sorry to so this symbol this symbol denotes like how the meter should be kept to take the readings. So there are three symbols in this, so I will just write it down here. So the this represents type of mounting. So if we have a vertical symbol like perpendicular symbol like this, and we also have some symbol like this, and also we have we have symbol like this, 60-degree or whatever, like angle can be anything. So if this is the symbol on that meter, that means that meter will be read when it is kept vertically. So let's say we had a wall, so that meter should be hanged there, like it should be placed vertically on that wall, and then we will be reading. So vertically reading should be taken. Reading should be taken. So that means the meter should be kept vertically, stick to that wall surface or something, then we can take the readings. If we have this kind of symbol, that means the meter should be kept horizontally on the ground, horizontally on ground, and then the reading should be taken. So and if this is the case, then that means like the meter panel or some that should be at the elevation of 60-degree, and whatever the angle is there mentioned, so the meter should be kept at that particular angle. Okay, so this is one thing. So if we are not doing like that, so we will be having some I can say parallax error, or we will be having some error, mostly parallax error for that. Not mostly parallax error, but we can have other types of error also. So this is like type of mounting. And then we have one more symbol. So I'm just saying this is not only symbols, there can be other symbols also, but these are the most natural, like most commonly occurring signals on the analog meters. So this star now means, so there are like different types of readings inside the star. So there can be an empty star, there can be 2 in it, there can be 0 in it. So this empty star means that analog meter, the insulation of that analog meter has been tested for 500 volts. If there is 2 in that, that means that the insulation of that analog meter have been tested for 2 kilovolts. And if it is 0, that it has not been tested at all. So maybe if the company is new, or that company is very local, or so they can do this also, like they will not test that for some insulations, but these are the standards. So no testing we can say. Okay, so there is also one in this, like there is 5 in this, that means 5 kV, tested for 5 kV. So that means that is more robust. Okay, so this was about the symbol. So this is so I just wanted to share this knowledge to you. So whenever you see these type of meters, you will be now getting to know, okay, these are the symbols and what they denote. So it will be good. Okay, so done with this. Now we will be moving towards first we will just go through the assignment questions. those were previous year's question, but I will just give you how I will just give you hints like how to solve them. And after that we will be solving some extra questions, and there was one doubt in previous previous session also, so I will clarify that also. So yeah, so these questions are almost similar, so I will be telling you about the concept, and then you can uh, proceed accordingly. So if we see the first question, so we talked about the measurement of high resistances in the application of like the measurement of high resistances. So this is one of the applications. So if you want to measure this insulator which is there in that skin color kind of yellowish color, and then we have a guard ring, and then we are trying to measure the insulation resistance. So the question is saying, while measuring the insulation resistance of a block of insulator that applied voltage is 4 kV. So we have this 4 kV here, and the current found to be 6 microamperes. So now this is for one time 6 microamperes in the presence of the guard ring. So when guard ring is there, that means the current measured is, I'll say this I equals to 6 microamperes. And if no guard ring, in the absence of the guard ring, then we have I equals to 7 microamperes. Okay, so we have length, we have width, we have height for this system. How much is the volume current? So now when they are talking about volume, first we'll have to understand that, okay, oops, what happened? Yeah, for first we'll have to understand so what is this why there is less current and why there is high current when we are using gartering, and when we are not using when we are not using gartering. So when we are using gartering, so what is happening, just some current is being injected into this insulator through this copper pad. This is copper pad, and what happens, some current goes from inside the insulator, that is the volume current we can say, and some current will be passing through the surface, okay, like this. Now if we have this guard ring, that guard ring is also kind of a conductor. So what will happen, this surface current will bypass like this, all the surface current passing from here. So this red means surface current, okay, surface current. So this will bypass through this, and it will come back to its voltage source, and this I will be only due to the volume resistance, okay, in first case when guard ring is there. So that means this 6 microampere current is because of only the volume resistivity or volume resistance. So if we say, so we had, what is the voltage we had? We had 4 kV, we had current 6 micro, so V by I is what, 4k by 6 micro. And what does this is equal to, this is RV, that is the volume the volume resistance. So they are saying volume current, so now you can say that is easily what is the volume current. So now I will tell what is happening without the guard ring. So if guard ring is not there, so what will happen, I will represent that with this current. So this surface current in case of no guard ring. Okay, so now I will just for the clarity, I will remove this red thing. Okay, now what is happening in case of no guarding, the current is going from here, it enters into this. So there is these, so volume current will be there itself in this case also, but now the surface current will pass like this, and since there is no guard ring here, so it will pass like this, and it will be received by this copper pad, and then this current will be here. So this will be having two currents, this plus this, okay, and this one. So we have two types of currents in this. That means we will be having I to O. Yeah, so this current, total current will be, I will be equal to the volume current plus the surface current. Okay, so we have currents because of both of this. So that's why also this current is being increased here. So that is 7 microamperes. So the equation for this will be, we will be having I4 kV divided by I total, that is 7 micro, which is equals to RV plus RS. Okay, so now this, and also RV is what, rho V, L, L in this case is W. So just keep in mind, don't commit mistake by taking L as this thing. So this is the length of the insulator. So this is W. Oops. Okay, yeah. So this is rho V, this is W, this is what, area of cross section. Area of cross section is basically, okay, I'll write that. Okay, I will write it this in red, since I have mentioned everything in red for this. So RV equals to rho V W, area is what, L into H. Okay, now the RS will be rho S, and now we have what, the this width is this 2W, and then we have periphery 2 times of L plus H. Okay, periphery of this one, so these and this, so this 2 times. So this we have the, so we have a formula for RV, RS, we have the formula for the resistance in case of no guard ring, we have formula for resistance in case of this guard ring. Okay, so we have all things, we can answer all these questions. 1 1 2 3 4 5 6 and 7 also. So 7 is simply like just changing uh, the the dimensions of that and how we can solve. So it is also easy, just manipulation. Now the next type of question, which is like common data for next 4 sub question. Okay, so this is kind of a Wheatstone bridge, and we can see here we have a voltage source PQRX, and what they are saying, at balance we found P equals to 80 ohms. Okay, Q equals to 70 ohms, R is 100, and what is X? So it is very simple, like okay, so it is simply P by X, Q by R. So this is the balanced Wheatstone bridge equation. So you can simply answer this. This is very easy. I don't think that will be difficult. So now, so they said the next question is, in the accuracy, if the accuracy of the registers are PQ, so they have given the accuracy, then estimate the inaccuracy of the measuring X. So now we have this equation, P by X equals to Q by R. So what happens, like so we have to measure the inaccuracy in case of X. So this is PR by Q. Okay, so one thing we can do, we can go, so basically this inaccuracy, uh, so that we can go simply by formulas, like the basic the conventional method, like if we have, so we have P R Q values. So P is equals to what, 80 plus minus 2%, Q is what, 70 plus minus 1%, and R is what, 100 plus minus 1%. Okay, so if we just go for this maximum values and minimum values and do the combination, so we can get all the possible outcomes of X, and then we can get all the maximum, we can get the maximum minimum values of X, and then we can say based on the percentage calculated from that how much inaccuracy will be. That is one method, that is conventional, that you should know. But the second method will be simple. So as mentioned in the class also, if we have like the accuracy for P is for 2%, so in division and multiplication they all get add up, all the inaccuracies get add up. So this is 2%, plus we have for R it is 1%, and this Q, since is in, but although it is in division, but still it will be get added the inaccuracy of that. So this will be 1%. So this is because of Q, this is because of R, this is because of P. Then we have percentage of inaccuracy in X, so we will get the answer. Okay. Now the next question. So if P and Q are fixed value resistors and R can be varied a step of 1 ohm. So they are saying that R can be, so basically delta R, the change in R is equals to 1 ohm. Then estimate the resolution of measuring X. So how delta X we can measure? So they have said that P and Q are fixed. So we had this X equals to P R by Q. So if P and Q are fixed, P and Q are fixed, so these two quantities are fixed. So we have, let's say, some whatever, like what was their value, 80 by 70. So this is fixed. Now if we are changing X by delta X thing, so this R will be also changing by some delta R. Okay, and what is delta R? Means if you are changing delta R by some value, then by multiplying with this constant, the X will be changing. So it is simple. So delta R is being changed in the step of 1 ohms. If we substitute that here, we will get the change in delta X. So this is also okay, this question. So we'll get the resolution of X. That means, like, what is the least value X can change itself. Okay, so now the next question. Estimate the required value of the source voltage E such that such that 0.1 ohm increase in X from the balance condition will produce a 10 microampere unbalanced current through the galvanometer. So now what they are saying, I'll just draw this thing for you. So we have this thing here, and this like this. Okay, so now they are saying, so they are telling us to calculate this E value. Okay, such that so we had x, yeah, it was here. So this x is, now we can say x prime, and x prime is what, it has been 0.1 ohm increase, so x plus 0.1 ohm. So whatever we calculated x in the first in this question, we can just substitute here, and we can get the x prime value, the new value of x, which have been increased here. So now this P, Q and R are constant as mentioned earlier also. So P 80, 70, okay. So this is 80, this is 70, this is 100. Now they are saying, so this, due to this imbalance in this X, what is happening, there will be a current flowing through this galvanometer, and that they have told us to be, that they have given us 10 microampere. Okay. So now we have a current through this. The galvanometer resistance is 1000 ohm, and they are saying this is a 1000 ohm resistance. Okay, so you know the issues. Okay, so now they are asking for calculating E. So we can go simply by like you can do KCL, KVL, you can do node analysis, you can do whatever you want. Or I think now it's easy. Now you have 10 microampere, so you can say, okay, the voltage drop in this branch will be what? Let's say this is A, this is B, this is C, this is D. Okay, so VAC will be what? This is current is flowing like this, 10 micro into 1000. Okay, so that will be 1 milliamp, 1 millivolt. So we have VAC as 1 millivolt. Now what is VAD? Based on voltage divider rule, we have E across VBD, and the voltage at one half of that branch will be, because of this E, it will be E into the resistance of that branch, that is X prime, divided by the total resistance of that branch, that means X prime and this 80 ohms. Okay, these are simple basic uh, techniques for solving or calculating voltages in a circuit. VAD, so we got VAD, and what will be VCD? VCD, this voltage and this voltage, this will be equal to, again that same technique. E is the voltage applied across this whole branch, VBCD. So we have E divided into the resistance of this branch, that is 100, divided by the total resistance, that is 100 plus 70. So we will get VCD, VAD. So now what is VAC? VAC will be VAD minus VCD, since this D is the common ground or common node to AD and CD. this AD and this AD and this CD. This D is the common ground, so we can just subtract that and we will get VAC. So we will get one VAC from subtracting these two values, and we have VAC already. So if we equate both of them, then we will get what is this what is E is. Okay, so X prime we got from here, so we only needed E, so we can get E from there. Okay, so now I think it's fine. So this is just like you applying your circuit theory knowledge in this. Now the next question. So if you have any doubts, you can just interrupt me in between and ask me, or you can write in chat box. So next question. So in all the sub question, assume, so they have said E is 120 volts, RL is 120 ohms. Okay, RCC is the current coil of the wattmeter, so that is okay, and RPC is the power coil meter, so okay, it is also fine. So now they are saying estimate the power supplied by the source in figure 0. So simple, this is very simple. So this is V and this is the current I going from this. So it will be the power supplied from the source PE. Let's say this is PE. It will be the voltage of that source and the current supplied by that source. That is easy. And what is the power dissipated? Power dissipated in the load will be I square R, or we can say V square by R also. Both will get same results. So I is same here, so in this case both will be same. Okay, so this is easy. Now the next question, estimate the power consumed by the load. So this that we have just said right now here. Now the next question, now they have attached a wattmeter between these two. So now what will happen, this CC is having a resistance of 12 ohms. This is 12 ohms and this PC is 600 ohms. This is 600 ohms. Now they are asking, now we connect an uncompensated wattmeter in figure 1 above, estimate the power supplied by the source. So we have, so now the power supplied by this is V and I. So now this I is basically, so basically if we have this I, we can get the power supplied by the source. So we will say PE, or we will say PS, power source, power from the source. Okay, this is PS, which is V into I. So V we have 120, I we don't know. So I will be what, the equivalent. So so let's calculate. So I will be diverted from here and here. So this will be I prime. This will be I double prime. Let's say, but we know what I prime will be. So I prime, I double prime basically is, so the voltage across this is 120, so that will be 120 divided by the resistance of this coil, that is 600. We'll get this thing. Okay, I prime will be what, I prime will be old, again we have this voltage 120 divided by the total resistance, that is 12, plus the load resistance 120, will get I prime. If we add both, we will get I, and we can put there in this and we'll get the answer. Okay, so estimate the power consumed by the load. Now the power consumed by the load will be PL, will be the voltage across the load into I across the load, that is I prime. So this current is I prime. Okay, and then so the load, the voltage across the load will be equals to total voltage, that is 120. So voltage across this is full, total voltage is 120 into the resistance of the load RL divided by RL plus total resistance of that branch RCC. We'll get VC, sorry, VL, and we can substitute here. We'll get PL. Okay, this is also fine. This was also fine. Estimate the wattmeter readings. So wattmeter readings will be what? Wattmeter reads V into I. So V is the voltage across its pressure coil, and I is the current through its current coil. So voltage across its pressure coil is this one, this voltage, this is what, 120 volts. So we have 120 here, and what is ICC, the current coil, that is I prime, this I prime current. Okay, so this will be I prime, so which we calculated from here, and then we can get W also. Now in next in the subsequent questions, we are just looking at the different connections of this wattmeter. So now this power coil has been attached across the load. So accordingly our things will be now the, let's say the source current is I. So this will be same as ICC, that is the current coil. Then we will be having I load, and then we'll be having I power coil current. Okay, so now simply again using that, so we should just be aware of, okay, what they are asking in the question, and accordingly we can solve. So we can so if we have 120 volts here, so what will be the voltage across this power coil? I'm just giving a general idea. So it will be simple, 120. So the equivalent, so this can be look like this. We have one supply source, so we have a resistance. I'm just converting the CC into a resistance, that is 12 ohm. Then we have one more resistance here, that is power coil, that is 600 ohms. Then we have our load resistance 120 ohm. So if we have to calculate the power coil voltage, that is this one, VPC. So that will be what, E we have, and sorry, we are calculating this current I. So we will be getting this resistance, full resistance. So this will be uh, yeah, so this will be what, if we need, so E will be what, I into the total RTH, let's say the equivalent, or IEQ, equivalent resistance of this thing. So it will be I, R equivalent will be what, 12 plus 600 parallel to 120. Okay, so this we have, and E is, so E we know this, that is 120. So 120 divided by this thing, we will get I. So that is the source current I. So similarly you can proceed further for different types of questions, similarly as we did in this first set of subsequent questions. Okay, so this same again, they are asking for the estimated power consumed by the load. That will be, in this case will be IL is the current now, so it will be IL square R. And estimate the wattmeter reading, that will be power in wattmeter, it will be VL or PC or PPC into ICC. So in this case ICC is I, the source current, and PC is what, the load voltage, which is this thing, uh, which we can basically, the load voltage we can calculate simply like, if we know IL from this case, then VL will be what, ILR, and that will be the power coil voltage. So this will be VL, ICC, this is the source current source. Okay, you can see in this diagram also. So you can solve these questions. And now again they changed the, they actually didn't change, but they actually added one compensating coil in that, and now they are asking for that same set of questions. So we have PC, we have C, current coil, we have power coil, and you can approach similarly as you approach in the previous questions, and you can get the answer for these also. So this is also again the power consumed by the load, power consumed by the source, wattmeter readings. Then they change the this thing, and I think this will be fine. So if you have any questions in this, then we can go through that. Otherwise I will go for the some of the extra questions which I have prepared. Yeah, so if you don't have any question, you can read the first question. So this was basically one student, I didn't remember the name, he asked me about, like, we used capacitors, multiplier capacitor, before this rectifying bridge circuit of a PMMC meter. So I told him like, okay, yeah, they use that, so it's good to like practice a question on that. And yeah, no, I will be giving an advantage why we use capacitor instead of resistor. So just go through the question. So the question is saying that a 100 kV 50 hertz supply is fed to a rectifier emitter using a bridge rectifier through a capacitor. So now what happens, normally you would have seen that if we have a sinusoidal source and we want to measure the AC, this AC signal from PMMC meter, so we use a bridge rectifier. And if we in order to, if you want to measure the voltage, and if in order to like increase the range of that meter, PMC meter, we use a multiplier resistance. So normally the circuit looks like this. So this is a multiplier resistance. We have a bridge rectifier circuit. Okay. This will be like okay, the current will be like this, yeah, and it will be like this. Okay. So this is our voltmeter. So either the this is the series multiplier. Now this RS can be used here or it can be used here also, so it will not matter, okay, it doesn't matter. So this is our sinusoidal source. So what happens, like this will increase the voltage range of this PMMC meter. So this is PMMC, and this diode circuits will rectify the signal, so we will get an output like something like this, full wave rectified sinusoidal signal if the input is like this. Okay, so this one. Now in this question what they are saying, they are saying that instead of this RS we attach a capacitor, and they are saying this is a series multiplier kind of. So through a capacitor, so this is acting as, instead of RS we are using this CS. We have again this same structure, and we have this voltmeter, I can say, yeah, PMMC meter. So we have a sinusoidal source like this. So what will happen if we calculate, if we are using a sinusoidal signal, so this, the reactance of this CS will be what, 1 by omega c. Okay, this one thing. So but here in this case, the, or we now if you're talking about resistances and capacitances, we can talk about impedance. So this, the impedance of this thing is what, RS, and the impedance of this structure is what, 1 by omega c. So if we have to like so basic idea of increasing the range of voltmeter is adding some value so that it can increase the net impedance of that in net impedance, so that there will be more voltage drop across that thing. So when we have seen this also, like when we had a galvanometer like this, we had a resistance like this, so it was measuring some, let's say it was measuring some 10 volts, but if we wanted to increase the range of this, so we added one RS here. So this in total was measuring 50 volts, so there was some drop across this. So this is basically an impedance. Okay, here also we are acting like, instead of RS we are using a capacitor. Okay, this is the simple funda. Now so if this is the case, now simple, now what is the question asking, the PMC ammeter of the rectifier instrument reads 45 into 10 to the power minus 3 amperes of current. So this is I, this I output will be saying I output, and now this I output will be what, this will be the average current. Why average current? Because PMMC meters read only average output, or only the average of the signal, outputted signal. So this we had as output signal, so the average of this will be, the average of this will be read by this PMMC meter. So I average is given by 45 milliamperes. It is given in the question. Okay, now they are saying the value of the capacitor is. So let's say if for one cycle, what will happen? This circuit will look like this. This, we have this capacitor, then this diode is off, this diode is on, this diode is off, we have this meter, and this diode is on, we have this. So the current will be flowing like this, something like this in one cycle, and in another cycle it will be flowing from these two. Okay, so in total this I average is what, the voltage average divided by the total resistance of the branch. So let's say impedance of the branch. I'm talking about impedance now because we are talking in terms of frequency in frequency world. Okay, so that's it. So the value of capacity. So V average. So now, so what is the V average of a full wave rectified output signal? So it is basically 2 Vm by pi. And what is Vm? Vm is the maximum value of this signal. That is this Vm. So this is V average of this. So we have 2 Vm by pi into Z. Now Z is what? Only we have capacitance. So we are neglecting the resistance of these diodes. So this is zero resistance, 0 ohms. Here also 0 ohms. So only this is having impedance value. Okay. So this will be what? 1 by omega C. Fine. So this will be 2 Vm by pi omega C. So this I average we know 45 milliamperes. Now what will be Vm? So they have mentioned 100 kVs. So if they have mentioned 100 kVs and they haven't said anything apart from that, that means this is RMS value. Okay. So in this equation, I will write like this: 45 milli equal to 2 into 100k root 2. So this Vm is basically, this 100k is the RMS value, so I am converting into the peak value by multiplying by root 2. So this is 100k root 2. Omega we know 2 pi, f is, they have given 50, okay, into c we don't know, that we have to calculate, and pi is pi. So this is the equation. So we can simply calculate C from here, and C will be equal to around 15.90 nanofarad. So yes, we can use multiplier capacitance also instead of multiplier resistance. So if you see anything in your questions like they have added a capacitor there, so then uh, you should not be worried, you can solve that easily also. But now the question is why we went for capacitor instead of resistor. So capacitor, the innate and the basic, when we use a capacitor, I think you would have learned or you will be learning in your further courses, or even I think in this course also, that capacitor acts as a good filter for DC signals. So what happens, I will, where should I, okay, one, I will add a page here. Hmm. So what happens when we are, so this was circuit, let's not talk about that. So we had a capacitor, so it is having a reactance of 1 by omega c. So if we give a DC signal to this, or a signal with having very less frequency, uh, if that is a DC signal, so if this is a DC signal, so then this capacitor will be what? This capacitor will be having a reactance of what? So omega will be 0, almost approximately 0, and 1 by omega c will tends towards infinity. So this will act as a open circuit for our circuit, for our rectifying circuit. Okay, so that means so there will be no DC signal being passed through this rectifier, or this is for 0, even for I think let's say till 5 hertz. But it will depend on the capacitance value. So 1 by omega c, if capacitance value is optimum enough, so we can set actually the capacitance value accordingly to cut the voltage, to cut the to make this impedance high. So what will happen if we see how will I say? So this is, let's say, frequency, and so this, let's say, 5 hertz. So if we kept this capacitor cut off as 5 hertz or something, so it will be, the impedance will be so high. Let's say this is impedance will be so high that this will act as an open circuit. So this will act as an open circuit for this bridge rectifier, and the signal will not be going there. So this act as a good filter. So that's why we use, sometimes we use a multiplier capacitor instead of a resistor. Okay, so this was the advantage of using this multiplier capacitor instead of multiplier resistance. So you can go to this. Now the next question. Yeah, just read the question and try to answer. So the question is saying that the following measurements are obtained on a single phase load. Okay, don't worry about that if you don't know. Single phase load means basically means single, like only one, only, which we normally only one phase is there. There's no two phase, no three phase. Okay, just only one sinusoidal signal or some signal is there. So then they are saying V equals to 220 volt, and they have this when they show like this, so that means that is the percentage error. Okay, and they have 220 plus minus 1 percentage of error, and for current they have this much error, 1 percentage error. For wattmeter they have 2 percentage of error. So if the power factor is calculated using these measurements, the worst case error in the calculated power factor in percentages. So normally I think you will be learning in this course only. I think in this fourth week itself, the power given by this is VI cos theta. So this is basically, this theta is the angle between voltage and the voltage of the pressure coil, and this is current is the current in the current coil of that wattmeter, and the angle between them is being given by this theta. So we have the power of this wattmeter as VI cos theta. Okay, so what will be the total error? So they are asking simple. So now if you know this concept, which will be very easy for you, so now you can easily answer this. So this is cos theta, this is power factor, okay, that you have studied in your basic electrical. So this is power factor. So what is the error in this W? It is 2 percentage. Now I have told you that if we are dividing or multiplying, the all the accuracies, or we can say all the errors, percentage errors will get added up. So this is 2% in this wattmeter, plus what is the error in this V? We have 1 percentage error, and what is the error in this I? We have 1 percentage error. Okay, so this all gets add up, and we'll have a 4 percentage error in this, and that is 4 percentage error in cos theta. So whatever the power factor measurement will be shown by this meter, or we will be trying to calculate, there will be error of 4 percentage in that plus minus 4%. Okay, so basically the idea is this, like just adding the percentage accuracies, or in another terms percentage worst case errors, to in if they are in division or in multiplying conditions, it will not matter, they will simply get added up. Okay, so this is fine. We'll move towards the next question. So just see this and try this. I'll give you some time. I also need some time. You can solve in meantime. So the question is you can solve parallelly. I'm just reading the question. A capacitive voltage divider is used to measure the bus voltage. So they had some bus voltage which I think will be of very high value. V bus, yeah, they are saying 100 kV. So V bus in a high voltage 50 hertz AC system. So they are talking about these power lines as shown in the figure. Okay, the measurement capacitors C1 and C2 have tolerances of plus minus 10% on their nominal capacitance values. So which is also mentioned here also. So they have 10 percentage of error. And then if the bus voltage V bus is 100 kV, so this is 100 kV RMS. Mentioned RMS. The maximum RMS output voltage V out, considering the capacitor tolerances is. Okay, we have one answer. I'll solve. Yeah. So the maximum RMS output voltage V out considering capacitor tolerances is, so simple. We will be going for this voltage divider rule. So we need to calculate this voltage V out RMS equals to what? V bus again, divided by the reactance of this, into the reactance of this, that is 1 by omega c2, divided by the total reactance of this, 1 by omega c2 plus 1 by omega c1. Okay, so it will be c1 plus c2. Now you need the maximum RMS current. So for that, what you will be doing, this is V bus we know, okay, that is 100k. C1 will be what? C1, yeah, C1 we have 1 micro plus 10 percentage of 1 micro, okay, divided by, now C1, we will now choose C1 as, so basically this means the values can vary in a range of plus minus 10% from this value, their main value. So now we can take 1 micro minus 10 percentage of 1 micro plus, so this C2 will be 9 micro minus 10 percentage of 9 micro. So why I took minus? Because if I subtract something in the denominator, the overall thing will be maximized. If we would have taken plus here, okay, if we would have taken plus here, then this denominator will become less and overall this denominator will become high and overall thing will be less. But we need maximum RMS output, so that's why we, instead of this, we took this thing here, and the answer is, yeah, 11.75 something, 11.75 volts. So V out RMS. Okay, so since they were asking for maximum, so what if they were asking for minimum? If they were asking for minimum output voltage, then it can go from 100k. So minimum will be what? 1 micro minus 10 percentage, because since we have to reduce overall value, so this will be minus instead of plus, into 1 micro divided by 1 micro. Now we will be using plus 10 percentage into 1 micro plus 9 micro plus again 10 percentage of 9 micro. So this term is for V out RMS minimum value, okay, and this was for maximum. So you can accordingly answer the question. I think this was fine. We'll move to the next question. Just read the question. Try to understand, and I think this is normal only. You can just try that. So the question is saying resistance is measured. So they are measuring some resistance value by the voltmeter emitter method, employing DC excitation and a voltmeter of very high resistance. So they have a DC excitation here, E, let's say and of a very high resistance connected directly across. So they are saying the voltmeter is connected directly across these R measure, R to be measured, we can say measure, or I will say RL, load resistance, which we have to measure that. So directly goes on, if the voltmeter and the ammeter readings are subject to maximum possible error. So and we have ammeter here, or we can since this is having very high value, so we can assume this is having no resistance of its own. So we can either connect emitter here or we connect emitter here. It will not create any issues because we are talking about an ideal situation. But if the resistance of voltmeter would have been like some value, like some some numerical value, some known value, then instead of infinite, then we cannot, then this both configuration will be having different readings, different this thing. uh, yeah, so now whatever the connection is, it will not matter. So we have I, this same I will be here, no I from there in voltmeter, and we have RL. So basically power is what, V square by RL, or it is uh, or we can say I square R, whatever power is this. Okay, so and they are saying the voltmeter reads 2.4% and ammeter reads 1%. So we can also say that power across this load will be Vi also, we can say, and the maximum possible percentage error in the value of resistance deduced from the measurement is nearly. Okay. So okay, so this Vi is the power from these voltmeter and ammeter, and we have I square R here. So this I think will be Vi by I square equals to R. So if we have to deduce like this, then but see, we cannot cancel like this because we are calculating the maximum possible error. So theoretically we can cancel, but practically the error will be getting added up. So we will be having for voltmeter readings how much we had, 2.4%, plus now all things will get add up. This will be 1 plus 2 times of 1. So total will be 2, 3, 4, 5.4 percentage. I think if I am correct, this will be 5.4 percentage. So I think this will be near to 5.4 percentage. Okay, understood. So yeah, so now we can move to the next question. Just read the question, and so I will tell you what limiting error is. Limiting error is simple: absolute error divided by the measured value into 100. Okay, so they are asking for limiting error, and yeah, so absolute error is what you have studied in this week 3, I think week 2 or week 3, that is the measured value minus 2 value. Okay, so now answer this thing. Previous slides one, sir. Okay, this one. Yeah, you can, if I have committed some mistake, you can tell me. Okay, so we will move towards the.
Hello, sir.
Yeah.
Uh, Here, a voltage into current method error. So 2.4 plus 1, 3.4 na current, sir.
Yeah, but then they are asking for the percentage error in the value of resistance. So I was also thinking like that, but that will be the maximum error in the power, I think, no? P equals to VI. So this is the power, percentage error in power. But if they are asking for the maximum possible percentage error in the value of resistance deduced from the measurement, so that's why I went for this. So I may be wrong, but and I also thought like VI. Getting my point.
Sir, once again.
So see, they're asking the magnitude of the maximum possible percentage error in the value of resistance deduced from the measurement.
So it is V square by R, na? V square is 4.8 plus 1.
4.8 plus 1 means, yeah, see, so we have power formula as VI, and which is equals to let's say I square R. Since we need the maximum percentage error in R value, so we will be having from this thing. So let's say you created this setup, then you have this V and I values, okay, with you. Now since this is an ideal situation where they are saying the voltmeter is having very high value, so it is ideal. So Vi equals to I square R. So Vi is from the ammeter and voltmeter readings. We have I also from the ammeter, so this will be I square, okay. So now they are asking for the maximum percentage error in R. So we have V is what, 2.4 percentage error. We have I 1 percentage error. Then we have I square, that is 2 into 1. Or in
Sir,
your
I cancel na, sir.
no,
I
that's what I
cancel.
said. That's what I said. Uh, see, mathematically we can cancel that, but uh, hmm, you may be right. But then I'm thinking like if mathematically we can cancel, but actually the errors are getting add up now. So that's what I'm thinking.
Sir, error gets added, sir. But ratio voltmeter, ammeter given V by I, so
Got it,
get
got it.
added,
Yeah,
sir.
you are right. You are right. You are right. You are right. So so we have separate readings for V by I, and yeah, we can simply, yeah, okay, yeah, you are right. So yeah, sorry for this. I'll just erase this thing. Yeah, so what is happening actually, we have some voltmeter reading, we have ammeter reading separately. So if we simply divide that, we will get the R value, and the percentage R error in R will be 2.4 plus 1. So it will be 3.4 percentage. Okay. Yeah, you were correct. Thank you. Okay. So if this is okay, yeah. So if this is okay for you, then we'll move towards the next question. Yeah. So the next question saying we have a voltmeter of 0 to 160 volt range, has an accuracy of 1%, full scale reading. So that means accuracy is now normally you should be now, by this time you should be now aware that whenever we talk about accuracy, it is the percentage error, worst case error. So now they are talking that this is 1% of full scale reading error. So whatever the reading, so let's say the voltage is 80 volts, now they are asking for the limiting error in that. So just try. So I have given this limiting error formula also. So first calculate the absolute error. You have the measurement value, that is 80 in this case. Yeah, because measuring at 80 volts, we are measuring the 80 volts into 100. Okay, now what will be the absolute error? So see, we if we talk about error, it will always be 1% of full scale. So 1% of full scale. So what is full scale? That is 160 volts. Okay, so it will always be 160 volts of 1%. That is 1.6 volts. So now what happens when we read this 80 volts? So now the meter looks like something like this. So this is 0 volts. This is 160 volts. Now somewhere in between, the pointer red here, the pointer denoted here. Okay, so this was 80 volts. Now, since the pointer is reading 80 volts, but there will be watt plus minus of error 1.6. Okay, why? Because they have mentioned that whatever it reads has an accuracy of 1% of full scale reading. So whatever it is reading, so there will be this 1% is what full scale is 1.6. So there will be plus minus of 1.6 volts in that measured value. Okay, so this, so although we are seeing 80 volts in that meter, but according to the manual of that meter, we can say it can either be 80 plus 1.6 or it can be 80 minus 1.6. Okay, so so what will be this absolute error which we are getting? This absolute error is this 1.6. Okay, so this absolute error will be what? 1.6 divided by 80 into 100. Okay, and if we solve this, then we'll get 2 percentage. Yeah, 2 percentage of error. This will be the answer. Okay. 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 So yeah, if this is fine, we'll move towards the next question. Yeah, this question. Just read that, and it is easy only, so you can answer that. I'll give you some time to read and answer. Like you can, yeah, solve. Yeah, before answering this, I wanted to tell you one more thing. Sorry for disturbance. I wanted to tell you one more thing related to this question. So normally, what happens, like commonly we have seen that they mention that accuracy. So it's a knowledge, just for like your knowledge. So they normally in the meters they tell accuracy of something X percentage for full scale reading. So this they mentioned. So that means like the error is constant. Okay, means the absolute error is constant. But the catch, what catch is, like so in this case itself, like we were seeing that it is 1% of full scale reading, that is 1.6 volts. Okay, so that was constant, that the absolute error was constant. But now you must have I think you must have heard this also, like they tell you that to read the values, to read the values try to read the values near to the full scale. So let's say if you were doing some experiment and you were trying to measure some voltages which were near, let's say, so for this example only we have 0 to 160 volt range. So you are doing some experiment and you are trying to measure some values which are near to 120 to 130 volts. So you know that somehow the values will be lying in between them, between these 120 130 values. And so for that, if you are taking this measurement, this voltmeter which is having a 160 volt range, then it is good in comparison to our voltmeter where you will be having a range of 0 to 200 volts. Now I will explain you why. This is a important concept, so you should hear this properly. Oh, okay. Landscape done. Okay. Hmm. So now let's say, so you have to measure something, let's say, and but you were measuring near 120. You know that it will come. Your measurements will come near 120 to 130 volts. Now you have two meters. One is from 0 to 160 volts. One is from 0 to 200 volts. Okay, and you have for both the meters the error is 1% of full scale. 1% of full scale reading. Okay, this is the accuracy of both the meters. So which meter you will choose for measurements of these values, which you know normally first meter. Okay, and why I will be giving the answer for that. So if you want to give the answer for that, you can write in the chat box, so others can also listen. So what is happening when we talk about, so when we said 1% of full scale is the error, so that will be 1% of, sorry, it was 10% now. Oh, sorry, 1%. Ah, fine. So it will be 6160. So it will be 1.6 volt. This will be the absolute error in this case. Okay. So in this case, it will be 200. That will be 2 volts. So here the absolute error is this. Here the absolute error is 1.6 volts. But if you talk about the percentage limiting error, so let's say we had a reading of 125 volts, which is somewhere lying in between this. So it will be, so what will be the error, limiting error for that? This is 1.6 according to this formula. Okay, and what is the measure value? 125 into 100. Okay, in this case, what will be the limiting error? It will be 2 volts divided by 125 into 100. Okay, so in this case, the percentage limiting error for your measurements is high. That means this instrument is giving high errors for your measurement values, but this instrument is giving less value of errors for your measurement values. That's why, as I told you earlier, people say try to read the values near the full scale. So this value was near to this full scale, but these measurements were not near to the full scale of this thing. So as you go away from the full scale readings of the meter, your error will increase. Okay, but if you go near to the full, if you are measuring near to the full scale of that meter, then the error will be decreasing. So it is a good practical practice in your future research career if you opt for that. So just try to go for a meter which is having a full scale, which you know your measurement readings will be near to that. Okay, so this was my point to make make the things clear for you. If this is fine, then I think for you also this was the same reason. But yeah, anyway, so this I wanted to tell. So now, yeah, back to the question. This question, yeah, just attempt this. So the question is simple. It's saying the experiment setup given below measures the value of unknown resistance in two steps. Okay, so we have V equals to 24 volts. So they are measuring basically this resistance unknown R. Yeah, so unknown resistance is R. So they are trying to measure that R. So first, like first case, they have V as 24, R is set as 400. So this is 400 ohms and S is 80 ohms. And galvanometer shows a deflection of theta. So we can say theta is directly proportional to the current flowing through it. Simple. So let's say if this was 30 degree, directly proportional to the current. So current will be what? V divided by the total resistance of this path. Okay, that will be what? R plus S plus G. Galvanometer resistance is there or not? I will see. When switch, so this is for first case. First switch 1, when the switch is in first position, switch position 1. For switch 2, It will be when switch is thrown to position 2, the supply voltage drops down to 22 volts. So they are saying that the supply voltage, so this was equals to 24 volts. Now it is 22 volts, and the galvanometer still shows 30-degree deflection. So this we have R. So now in this case we have capital R plus G. Now since they haven't mentioned about the galvanometer resistance, we can neglect that. So simply if we divide both, we will get 1 equals to 24 divided by R plus S, 22 R plus R. So we know R both in both cases, since this thing is constant. So this is 24 400, yeah, 400. R was, yeah, plus S was 80 first case, 400 plus R 22 1. Okay, so you can get R from here. Simple. If this is clear, we can go to next question. Oh, sorry. Yeah. The next question, just read it and try to answer. It's simple. So they are talking about what is resolution, sensitivity, accuracy, precision. So I think resolution, precision, I will say, uh, not resolution, accuracy and precision. So there might be confusion in this. So there is a very famous example for this. Uh, so first of all, we'll tell the answer, then I will tell you the. Okay, first I will tell you the famous example. So what is, like, if you are trying to hit arrows on a dartboard. So if all your arrows are like hitting here, let's say in first case, in this case, like arrows, or wait, oops, sorry to go. So let's say in first case all your arrows are here, all your, like, you put things here. Then in the next case your arrows, this is the third case, and in this case you have let's say uh, so case 1 2 3. So precision is like I'll say how, like, how repeatedly your things are coming. So like how you again and again you can. Okay, we have one answer, D. Okay, is, for D it is okay. We'll tell. So while learning, we'll know the answer. Okay, so what is happening? So precision is basically like how again and again you are repeating that value. If you have some system, you again and again how you are repeating the values. And accuracy is like how close your values to your what I'll say, to your true values. That is accuracy. Sensitivity is like for a small change, like what, like for some change, how well your system is behaving based on that. And resolution is how small your system can measure something. Okay, so if we talk about that, so precision is, as I mentioned, reproducibility of measurements. Sensitivity is like so ratio of response, I can say. Okay, yeah, so like if you, how well your instrument is responding. Accuracy is like closeness with which the instrument reading approaches the true value. And resolution is, because third is the only option left. No, but yeah, we know why it is smallest change in. So now but yeah, answer is D. But now the thing is, if by giving this example you will at least have an idea between these accuracy and precision. So in first case, almost all the darts have been hit in this area again and again, so that means this was precise. this thing was precise, but was this accurate? No, it was not accurate, because accuracy is, if this would have hit in between the bullseye, okay, then it would have been accurate also. In second system, if we see, although we are hitting some darts at the center, this, at least this system is somewhat accurate in comparison to this system, but it is not precise, because we are not, again and again we are not getting the same value. Sometimes values are here, sometimes it's here, sometimes it's here, sometimes it's here, sometimes, but it's near to the main middle value. In this case, all we are again and again hitting in the middle, so it is near to the true value, that is in the middle, and also they are close to each other. So this is accurate, the most accurate plus precise. Okay, so this is what we need ideally. uh, so this is the difference between accuracy and precision. I think you would have learned about this example, but anyway, I just gave you. Okay, so this is done. Now we'll go to the next question. Take your time and answer this. So I will draw the, okay, I will draw the, oh, I have to draw the circuit for you, sorry for that. So this we have circuit like this, we have, this is VCD, this is D, this is C, okay, this is like some resistance, this is switch. At t equals to 0 we have switch on this thing, and this is which it is, oh, this was 1.5 kilo ohms, R1 was 1.5, this is R1, R2, this is 1 kilo ohm, this is 1 kilo ohm, this is 1 kilo ohm, this is 3 kilo ohms. Okay, this thing, upon closing the resistance of the arm AD. So this is A, this is C, this is B nodes. Okay, I think, yeah, I have given, and this is 10 volts. Now you can attempt this question. So they are asking basically, this is a Wheatstone bridge and the switch is initially open, okay, and the voltage between the point C and D is VCD. So when switch is off or open, we have VCD between the point C and D. So we have some VCD voltage, okay, and when switch is on at t equals to 0, so this was t less than 0, okay. So we have a change in resistance. So this, so basically this was R1. So initially here R1 was what, 1.5k. Now R1 prime, the change in R1 will be what, 1.5k parallel to 3k. So so this is, so delta R1 will be what, R1, so it will be R1 minus R1 prime minus R1 modulus, okay. We don't know which is higher value, and the voltage between C and D changes by delta VCD. So initially it was VCD, now it is delta VCD, it has been changed to VCD, so it will be VCD prime. So in this case the value was VCD prime minus VCD, so this is VCD prime. So we simply have to calculate the sensitivity of the bridge defined as this. So sensitivity of the bridge is sensitivity equals to, its given, delta VCD divided by delta R1 modulus is dash. So yeah, so this is the overview of this question. So we see, so see, we know this R1 prime, we know R1, so we can get this del R1, not an issue. Only thing is that we'll have to calculate this delta VCD. So what that, uh, VCD is what? VCD is this between this two. So we can simply use voltage divider thing. So VCB first, VCB will be what? Equals to 10, the total voltage across VAB into 1k the resistance divided by total resistance 2k. So this is before like we are switching on. So VDB will be what? 10 into 1k, yeah, 1k divided by 2k. So we'll get this as yeah, 5 5. So 5 volts. Oh sorry, this was 1.5, so this will be 2.5. Sorry for that, because this is 1.5k, so this will be 2.5, so this will be something 104 volts. Okay, this will be 5 volts. So we will have VCD as VCB minus VDB. Simple. So we'll have minus 1 volts, sorry, 1 volt plus 1 volts. So we have 1 volts there. Okay, and now what is VCD prime? Again you can do the same thing. So VCB will be 10 into 1 by 2, that is 5 volts. VDB will be, now it will be 10 into 1, obviously, yeah, 1k divided by 1k plus parallel of, or we can say R1 prime. Okay, so if you have R1 prime, you have calculated from, you can easily calculate from here. Easy, simple. So we'll be having VCD as whatever the 5 volts minus this value minus VDB, you can get this value. So this will be VCD prime. So then if we have VCD prime, we have VCD, we can get delta VCD, then we can substitute here. Easy. Okay, you can calculate. So our answer will be 2 millivolts per ohm. So you can do on your own later. 2 millivolt per ohm. Okay, it is easy, simple voltage divider things you have to do. Nothing much. Now the next question, just read this and answer. So strain gauge is basically if you apply strain on that, so the its resistance will get changed. So that is that simple thing that you can represent that with this a variable arrow and this thing. So that is basically a variable register. Yeah. So they are saying that without any load as Rs equals to, so say they have, okay, this is Rs. If it is not clear, yeah, this is Rs. So we have listen, without any load. So if that on that strain gauge there was no load, there was no pressure, there was no strain, then its resistance was Rs equals to 300 ohms. And similarly for others, like it was R1 equals to R2 equals to R3 equals to 300 ohms, and this was the balance condition. Obviously this was the balance condition for the bridge. The maximum, now they are asking the maximum permissible current to the strain gauges. Now so they said like maximum current which can be passed so that this strain gauges, that is, so it is like this is Rs. So maximum current can pass through this is 20 milliamperes. Okay. During certain measurements, so they are now measuring something when the bridge is excited by maximum permissible voltage and the strain gauge resistance is increased by 1% over the nominal value. The output voltage V naught is. So they are saying they applied. Okay, see, yeah, we'll get through that. See, answer is yeah, C, correct. Uh, yeah. So they are saying maximum current which can be passed, so that maximum permissible voltage they have given. So that indirectly they are trying to say they are trying to pass the maximum current from this drain gauge. So now what is the condition of our circuit? So we have this RS prime which is equals to basically 300 plus 1% change they have done. They have added 1% thing. The change is 1% over that nominal value, that is 300, and we have this 300 here. We have this minus plus. Okay, this was this. This was 300. This was 300. This was how much? Yeah, that we don't know. We not that we know. Yeah, no, we don't know. Okay, VI. So based on this VI, we need to calculate V naught when we give this maximum permissible voltage here. So this is only can be done when we are giving 20. That if this is maximum, that means this there will be maximum current flowing through it. That is only. So this was the catch in this question. Rest of the question is easy only. So now they are asking for the V naught voltage, and so we have 20 milliamperes. We can simply do A B C D. So we will get like 20 milliampere is this, so this will be 20 milliampere. So you can simply get this as Vi. You can, so maximum voltage you can get as, so 20 is flowing through this branch, so it will be 20 milli into this will be what, 303 plus 300. Okay, so you will get Vi. This is maximum voltage, input voltage. So based on that you can get VDC. VDC is what? VDC is VI, that this VI into this resistance 300 divided by the total resistance, that is 300 plus 300. So you will get VDC. You have you can get also similarly you can get VBC, but you, since you have current, you know current, that will be 300 resistance of this into 20 milli, that is the current flowing through this branch. So you will get VBC also. So you can simply subtract both of them, and then you will be having V naught is VBC minus VDC. You will get that is 29.85. Okay, simple. Only catch was like once they give that maximum permissible voltage, that means they are giving increasing the voltage till this value, that so that such that there will be maximum current flowing through that strain gauge. Okay, so this was fine. We will go to the next question. Answer this question. Wattmeter, we are looking at wattmeter. Shown in the figure, the wattmeter reads. What will it read? Uh, so if you know that like properly the concept of wattmeter, so wattmeter is basically, so you will, so this is the starting of wattmeter questions, not in this session, like in your course also you have started just with the wattmeter. You will be looking at three phase wattmeters and lots of wattmeter things. So, and you will be facing a lot of questions on that also, but the basic idea of like how what wattmeter measures, it is measuring basically, I will say like this. So this is like the voltage across its potential coil. So whatever the voltage is there across the potential coil, it will measure that. It only knows that, nothing else it knows. And the current from the current coil. Okay, and the vector, that is the dot product of them, because for a single phase it is VPC ICC cos theta. So that's why I said vector. Okay, so there is a dot product. So just keep this thing in mind. You will be able to solve all types of questions based on wattmeters. Okay, so just you have to calculate the voltage across the potential coil, and second thing, the current across the current through the current coil. That's only you have to calculate. So this will be like so now what is the voltage across this potential coil? In this case it will be, we have this. So this is the VPC, voltage across the potential coil, and the current is this ICC, this ICC. Okay, so this is the current flowing through this. So now what this will measure, so this is VPC, you know, this ICC. So now if you observe, what is the power across Z2, power of Z2, it is the voltage across it, that is VPC, okay, into the current flowing through it, ICC. So, and this is what the wattmeter reading is also saying. So basically this wattmeter uh, connections are basically measuring the power consumed by Z2. Okay, so just look for the voltage across the potential coil, what it is measuring across which element, and the so just yeah, and the current from the current coil. Just focus on that if you are thinking of wattmeter, if you are looking at wattmeter questions. Okay, so I think there's another question like this. No, okay, so this was the answer. Okay, so now we'll go to the next question. While I think I'll have to make the circuit for this. Yeah, I'll make the circuit for this. So we have something like this, something yeah, like this. We have one ammeter here, we have one voltmeter here, and we have a load here. So this coil was having 4 kilo ohm resistance. This is a power coil of, so this is a wattmeter. This is a power coil of this wattmeter, and this is the PC, the resistance of the power coil. This is CC or CC, the resistance of the current coil, and it is zero point 0.2 ohms. And we also have zero point 0.1 ohm for this ammeter, and we have 4 kilo ohms for this voltmeters. Okay, so now they are asking, while measuring power absorbed by the load using the arrangement shown in the figure. Now you can see the figure. So Z2 must be impedance now, sir, for cos of angle between them is 0. It's just a representation. There's nowhere mentioned like it is impedance. Yeah, resistance. Yeah, yeah. But since they have just mentioned Z2, so, and they are not talking about any angle between them, so you can just like say okay, okay, it is a resistance or something like that. Yeah, but yeah, when you will be like uh, so there will be, so I will, in next session I will be definitely coming with some. So since you haven't covered these single phase, three phase wattmeter type concepts in your weeks, in your sessions and lectures sessions, that's why I didn't come up with that question. But I will, next week I will come with that questions, and then you will be getting a full idea of how wattmeters can read. Okay, so yeah, so this question, while measuring power observed by the load, so they are saying obtained values for voltmeter was 150 volts. So they measured voltmeter reading as 150, and the current reading was, so basically the current reading means this current I which was flowing through this I, and the voltage was this. This was 150 volts, and this current I is 12 amperes. Okay, if the load power factor is unity, so now this load power factor is cos theta equals to 1, the wattmeter reading will be. So when they say the load power factor is unity, that you can see, you can consider that to be a resistance. Okay, So now you have to answer this. So they're saying they are asking for the wattmeter readings. So just remember wattmeter readings is forget about, like, just don't be afraid of whatever the connections of that wattmeter are. Just focus on what is the voltage across power coil into the current from current coil. Just focus on that. You will get answer to any type of configuration. So in this case, this I which they have given is same as ICC. Why? It is because it is flowing from this current coil. Okay, so ICC is same as that of the measured from the ammeter, that is 12 amperes. And what is VPC? VPC is basically this voltage. VP, this is C, let's say. So this VPC, but this is actually calculating this whole thing voltage. So now how simple we can, VPC will be what simple we can do. So we know the current from this branch, that is ICC or I, which is 12. So 12 into zero point 0.2 is the resistance, is the drop. So zero point 0.2 is the resistance plus zero point 0.1 is the ammeter resistance. So we are going like this. So and this is what plus, and the next voltage drop is what, 150. This we already know. Okay, simple KVL we have done. Okay, we have one answer 1800. Okay, I will check. 1800. No, it is somewhat. You need to you need to consider the resistance of these also. So I think you missed that. So that's why it's 1800 for you. But yeah, the idea is this. So VPC we have. So uh, yeah, I think yeah, you did 12 into 150. So you did 12 into 150. But that is I think wrong, because we have this resistances also. I again and again I'm saying focus on the like the voltage across this potential coil. So now in this case, the potential, this power coil is measuring the voltage across this RCC, this ammeter, and this voltmeter also. So that's why it will be like this. Okay, so this will be 153.6. So the total watt power will be 153.6 into ICC is 12. So that will be 1843.2. Now when you are like solving wattmeter questions, so you cannot say, okay, if I have an answer near to that, it is correct. You should be having the same answer, like near to that. You cannot say it is, if it is 1820 then it is correct. No, because that's what we are dealing here with. These are having small values of resistances, but still they are making an impact, and the person who's making that question, so yeah, they will be expecting that only from you, that exact answer from you. Okay, so this was just based on the, because this was just explanation was based like for the gate question. So if there is a range for the question, so they are expecting only plus minus a point something, one or two, something like that from you, deviation of the answer with respect to the gates. Otherwise, yeah, otherwise also it is yeah, you should be getting the exact answer. The reading the what is shown in figure is, this is a very difficult question if I don't give you the figure. So I will give you the figure, wait for that. So this we have J10, this is an inductor, this 12 ohms, J10 ohms. This is this is a current coil, this is potential coil, this is a wattmeter in this case. Minus J6, this is 8 ohms. Okay, so this is the circuit. We have a supply here which is 200 volts. Just they have given 200 volts. Yeah, so you have to calculate the reading of the wattmeter. So this is wattmeter. Okay, so they have mentioned the ml. This is the convention of this coils, CMLCV. Okay, so now yeah, you have to calculate this. Yeah. Now your concept of phase will come here. So wattmeter readings, wattmeter measures vi cos theta, and this is also, we can say, real power. I think you must have read this in your basic electricals. So there are, the total power is like vi cos theta plus vi sin theta. So this we say as reactive power, and this is active power. And we are for we want to like the wattmeter reads such that it basically the average power, which is vi cos theta. So yeah, so you will, in this case, you will have to be sure about the angle between voltage, the given voltage, and the current. So for that, like although you should have the good knowledge of phasors, but if you are like, if you are not sure about that, first of all you should be sure about that. But if you are not, so simple, what you can do here, so since this is rms value, and this is also vrms, irms cos theta. So this is the formula for wattmeter readings. So now what is there, like, so you have, so this will be the voltage across the power coil. So this is this voltage. So we'll have to calculate this. So first we will simply calculate the current of the whole circuit. So what will be the current? irms, this, let's say irms. Simple, just don't afraid of if there is an inductor, if there is a capacitance. Okay, just if there is like they haven't given you the reactances of those inductor or capacitance, then you just convert them into their reactances, and resistances are resistances, and then you try to solve that. So just see how simple this question is. So irms is what? The voltage of this voltage supply across, and divided by the whole impedance of this circuit. Okay, and since they haven't mentioned any impedance of this, okay, we have one answer. Okay, that is I. Yeah, but we should be careful about the phasor. It should, it should have some the value is correct, but we need that angle also, theta. Okay, so yeah, this is 200 divided by the total impedance of the circuit. So since we don't have any, they don't have mentioned about they didn't mention about this power coil resistance and current coil resistance, so we will neglect that. So we will say this cc is having 0 ohms resistance, and this power coil is having almost infinite. Okay, we will not care about that. So this is now the total impedance of the circuit will be what? 12 plus simple j10 plus 8 ohms minus j6, simple. So this will be 200 divided by 20 plus j2. So normally you will be having your scientific, correct, negative 11.8 is the, yeah, 11.3, 11.8, yeah, it's fine. If that is the phase of that, but that is current, we need power, we need this meter readings. Okay, so yeah, you are on the right track. So yeah, so what we are doing, irms will be 200 by 220 plus j2. So this is the current from this in the circuit. Now no current will be going through this path, all the current will be going through this. So what will happen, wattmeter reading will become the power coil voltage is what? This voltage. Okay, this voltage. So that will be what? We have irms, we have the impedance of this, that will be the voltage drop across that. So that will be 220 plus j2 into 8 minus j6. And what is irms? We have just calculated 220 plus j2. So if we are trying to solve like this, so this will be the real part of this. The real part of this will be the wattmeter reading. So if you are just trying to calculate in the phasor, that will be easy for you, because then you won't have to like calculate separately the theta value. Just solve this thing. You will get something like some real part plus j sine like some imaginary part in this, and your readings will be the real part of that. So you will get, you will have to focus on real part, that is the wattmeter reading. So for your convenience, so so I'll just write the answers if the concept is fine. Yeah, So IRMS was in phases. I'm writing 9.8 minus 11.3 amperes. One answer. V was the power coil resistance 98.05 angle minus 48.17. Okay, this is power coil resistance. So if we have this, we have this, so we can simply substitute in this. So wattmeter reading, real part of that wattmeter reading will be 9.8 into 98.05 into cos of 48.17 minus 11.3. So this is the reading, which will be equal to 0.768 kilowatt. Sorry for the this thing. Angle for voltage, please do. Okay, I will do. Wait, I'll add one page. Add one, yeah. Landscape done. Okay, yeah. So for the voltage, we have voltage is what? For the power coil voltage, that is this voltage, power coil voltage, it is IRMS into the resistance of that branch, which is 8 minus j6. Okay, 8 minus, so this is the impedance. Okay, and so we are dealing in this all the polar coordinates. This is IRMS, this will be also polar. So it is basically what it is, 200. So this we had 220 plus j2, 8 minus j6. So now it's all mathematical calculations. 100, 10 plus j, 8 minus j6. So I'll just use my scientific calculator. Wait for that. So it will be 100 into 8 minus 6 shift iota. This will be 10 plus shift iota. So according to my calculations, it is did mistake in numerator angle. Numerator angle. I or you? I did or you did? I don't know. Okay. Okay, okay. Cool, cool, cool. No issues, no issues. So yeah, so this is, we have 73.26 minus 67.32 J. So we have this. If we have to convert this into what that complex part, wait, answer shift complex polar, yeah. So this will be 99.5 angle minus 42.58. Okay, uh, 42.58. Okay, so yeah, you can calculate this easily, polar coordinates conversion and all. So now you have voltage, I think I mentioned here 98. 98. Okay, just check on the calculation. Yeah, but I think answer will be this one, 0.768 kilowatt. Okay, so if this is okay, then I think, yeah, this last question will not do it today. I will just, I'm giving this as a first for screen. I'm just freezing for 1 minute, not 1 minute, 10 seconds. So in YouTube lecture, you can go through that, pause that video, and then you can do it as a homework. So this will be a homework. I will discuss this in the next section, next class. So okay, so yeah, so I think this is enough for like pausing for you on a YouTube, and then you can check this. So this question, yeah, now you can easily solve this. So this is the last question for today. So a potential coil of the wattmeter when connected in the following sequence. So first sequence is V connected to A. I mentioned earlier also, just focus on the potential of the potential coil and the current of the current coil. That will lead you to the wattmeter reading. Okay. So now if we are focusing for first part, V connected to A. So this V is connected to A. This is the first part they are saying. So this would indicate the power consumed by. So in the first case, what will happen? So the power coil will be, so power coil will be measuring the voltage across. Okay, we have one answer. We'll see. We'll see. We'll see. So we have so V power coil is what? The voltage across power coil is actually measuring the voltage across Z1 and Z2. So that is VZ1 plus VZ2. Okay, one thing. What is the current through this current coil? So it is the current coil. Current is the same current which is passing through Z1 and Z2. So ICC is IZ1 equal to IZ2 because it is in series. So the wattmeter will read VPC into ICC, which is VZ1 plus VZ2 into IZ1 or IZ2. Yeah, that is same. Okay, so I'll just write ICC. Hmm. So for this one, so this would indicate, so it will calculate power for Z1 and Z2 in first configuration. In the second configuration, if this is in B part, it is not here. Similar, so going with the same logic, it will be just calculating the power across Z1. Second case will be Z1. Third case Z2. So the power will be, if third case is C connected to B. So this is connected to, okay, B. So voltage is across, and okay, V is connected to A then. Okay, normally. So in the third case, C is connected to B, V is connected to A. We have, so we have potential across Z2. Current is going through Z2, same, that same current is there, so it will be Z2. Answer will be A. Yeah. So this is for all for today's session. I hope you get something today. And I don't know who asked me that question for capacitance of that multiply capacitance thing. So I have solved that in the, yeah, in the starting that question, like having a multiplier resistance. You can see okay, you okay, fine. So I have explained that in the starting of the lecture, so you can see that in the recorded video. Okay, so yeah, so all for today. I have given you this question as a homework. You can try that. Give your recording link in chat. I have given that in, so this video will be, I will be uploading in a while, but I will give you the uh, YouTube link. I have to give now, channel link now. Wait, I will give you, but I think I have posted on that forum also, but okay, no issues. Switch account. Hmm. Yeah, so I think this link will, uh, yeah, I think, yeah, this will work. Yeah, welcome. So I have given you the link. You can go through that. And I will encourage again to attend live sessions so that it will be good. If you want to ask some questions, you can ask me in that. And yeah, I'm trying. I will start giving some fun facts in the starting of the session. Today also I gave something funny, I think unique in the starting of the session. So you can go through that session. I will be uploading in a while that this live session, so you can just check that. And I will try to give something unique on the every starting of that video. So yeah, all for today. Thank you for, yeah, thank you. Okay, so I will be ending this session. Thank you.